Good morning, good afternoon, depending on when you are listening to this particular recording. Uh, Previously in week 2, we talked about different encryption methods. Okay, we talked about block versus stream. Today we're going to talk about, in week 3, talk about public key cryptography, and it's kind of widely used and is the basic way of having information that uses keys. What do we need to do in order to get the key as far as needed for the encryption? What do we need to do to get it to the source that needs it, and so they be able to encrypt it? And that's what we're going to talk about, public and private keys today. Today's lecture is about ideas. Okay, so there's going to be some math, but we're not basically building a math course here, but so we're talking about the ideas on what we need in order to have what we need in place in order to encrypt and decrypt information in a public-private key scenario. Okay, well, one of the things that we'll be using is prime numbers. I'm pretty sure most of you at some point in your math course talked about prime numbers, where a prime number is a value that can only be divided by 1 in itself evenly. And so a prime number here, say, is a number greater than 1. It has to be greater than 1, and can only be divided by the number in itself. Examples 2, 3, 5, 7, 13. And we can go infinite number of prime numbers, some very big numbers that we're going to be talking about using. The key thing here, I'm going to kind of highlight here for everybody, it says every hard to break apart. They are easy to multiply. That's the prime numbers. They're easy to multiply, but they're hard to try to figure out how to break them apart once they get very large. For example, it's easy to calculate 7 times 11 is 77, okay? But only if you give the number 77 and ask, okay, well, what 2 prime numbers did you use in order to get it, okay? That takes a little more effort. And the more effort that it takes for someone to get or break the code, okay, the more then it's more likelihood that they may give up or may take too much time for them to figure out, what these particular prime numbers are in order to crack the code. Modular arithmetic, math that wraps around. Okay, you'll be seeing a lot of modular arithmetic. And what basically modular arithmetic will do for us is basically take a very big range and using modular arithmetic, put that range in some finite time space. Okay, so, I might have a million bytes, but once I go through modular arithmetic, it may come out to be 14. Okay. And we'll talk about that in a little more detail here in a second. But we have modular arithmetic, modular addition. If it's 9 o'clock, you add 5 hours, you get 14 o'clock. You wrap around, that's really 2 o'clock. Even though military time, you'll see terms like 1200, 1300, 1400, where basically that is an attempt not to wrap around, but it's used very much in the military. Modular addition, modular subtraction, modular multiplication. Multiplication, you can wrap around when it reaches a limit. Cryptography uses this kind of math because numbers stay within a fixed range. Yeah, that's what it said. I can take a number that's very big and keep it within a fixed range that's more doable and more easily manipulated. Patterns become hard to reverse. Okay, since I'm basically keeping things in this narrow space, trying to figure out where it came from, similar to what we talked about for random numbers, it's going to be difficult. And what we want to do is something, as we said, keep in mind, we want to make encryption easy to do, but very hard to break. Okay, that is our main goal. Math is predictable for a computer, but confusing for attackers. Yeah. If I had a math computer program, yeah, I probably could bust it, but just a regular hacker, it's going to be very difficult. The problem, public and private key. Okay, we're going to talk about what that solves. Before public key cryptography was existed, there was a big problem. If I had two people that wanted to communicate with each other and they had agreed on a secret key, how do I get that secret key and keep it secret in sending that to them? So if someone intercepted the key, the encryption was useless. The problem is that public key cryptography, where two different keys are used instead of one. We're going to talk about having a public key and a private key. RSA, we've been talking about this in a little more detail as far as your project is concerned. It's Reverse-Shamir-Adleman algorithm. Okay, so the RSA, commonly called, the RSA public key encryption system, uses two related keys. It uses a public key, which can be shared with anybody. Okay, no big deal. But a private key, which must be kept secret. The private key is what takes that public key and basically decrypts that information with the private key. The keys that we are using are usually very large prime numbers, and it uses modular arithmetic that we talked about previously. Okay, how RSA creates keys? Conceptually, here's what the process is. Here's the idea behind RSA. Two very large prime numbers are chosen. These prime numbers are multiplied together. The result helps create a public key for encryption and a private key for decryption. The important idea is this: the public key can lock the message, but only the private key can unlock it. Okay, so I can use this public key to lock any number of messages, no matter what length, no big deal. If two people has the same public key, okay, as long as we have different private keys, we can keep that information secure. So here, even if the attacker knows the public key and the encryption method, they still cannot figure out the private key, without breaking it apart, using very large numbers. Very difficult to do. Okay, how RSA encrypts and decrypts the data. Okay, encryption, the sender sends the recipient's public key. The message is scrambled using a modular arithmetic, and then result is unreadable encrypted data. The decryption, the recipient uses the private key. The math reverses the scrambling, and the original message is recovered. RSA is usually used to protect small pieces of data, such as keys. Okay, not entire files. It's not normally used for that. Why large prime numbers matter? Okay, RSA is only secure when the prime numbers used are very large. Okay, if the prime numbers are small, attackers can break the encryption. They can figure out how to get in and find out what they need to decrypt a particular message or key. If prime numbers are large, breaking the encryption would take more time than computers realistically have, which in the case of computers, that is going to be a very long time. That is why modern RSA systems use extremely large numbers. One of the things in the project, you'll be talking about using big values, big integers, okay? Because when we're going to do the multiplications, we're going to be using very large numbers in your project. Okay, what is elliptical curve cryptology? Something used. It's another type of public key, private key cryptography. Like RSA, it uses a public-private key, allows secure communication without sharing secrets. However, instead of using large prime numbers and factors, it uses mathematical points on the curve. Okay, that's cool. Okay, so here we're talking about how elliptical curve cryptography differs from RSA. Okay, here's the key idea students should remember. RSA security is based on the difficulty of breaking apart large numbers. Elliptical curve cryptography is security is based on the difficulty of solving math problems to figure out a particular point on the curve. Yeah, kind of advanced stuff. Again, we're not going to get into the actual mathematics where we we'll do something like that if we go into advanced cryptography course. We'll get into the detail. But here we're just looking at the methods, okay, that can be used to do so and the different models we can use. So elliptical curve cryptography is popular because it can use smaller keys, it provides strong security, and it's fast and uses less power. Okay. It makes especially useful for mobile devices, small devices, security web connections, anything that's on a small scale that we need the same public key, private key uh, availability to us for encryption and decryption. Week 2 summary. Okay, at the end of this week, you should understand prime numbers are the foundation of modern cryptography. Modular arithmetic allows numbers to be wrapped around. Okay, so basically takes a large range and moves it into a smaller window. The RSA algorithm uses large prime numbers, and large prime numbers are essential to make any RSA work. Okay, elliptical cryptography offers similar security, but with smaller keys and better efficiency. Okay, so if you can explain, kind of what is the purpose, if you can explain the ideas without having to use a formula, okay, what the basic idea is behind RSA and behind the elliptical curve, that is what I want you to get out of here this now. Just the general processes of what we're doing, okay, in order to take input, encrypt it, output it based on decryption, okay, and what are the methods we're using to do that. Okay, as in every week, your project is going to kind of expand on this. So where this is kind of an introduction of the various concepts, your project is really going to be delving more deeply into giving you some practical experience and to be able to see how these things are used based on this conversation we just had. Okay, have at it, and I'll see you next week in week 4. Have a good one.